Now we're ready to define the integration of a positive measurable function. So for this, let's consider again a measure space, and let's let f to be a non-negative or positive measurable function from x to r. So measurable again means Borel measurable. And let's define the following. Let's define the integral of f. Let's use this notation, the integral of f d mu, where mu is really stressing the measure on the space. And I define it to be the supremum of all the I functions. So here I require phi is a simple function that's between 0 and f. And I compute the I of phi, which we defined in the last video. And I take the supremum of all such simple function, okay? So this is my definition of the integral, and just a notation issue. So if I have some measurable set A in this curly A, then sometimes I will write integral over A of this function f. What I really mean is that I'm integrating f over the subset A, or you can think about it as you multiply f with the characteristic function, and you treat it as, well, this is a measurable function again, and you do the integration. Okay, so it's really another way of thinking it is really you're integrating the f, but you do the mu restricted on A. We define it as on our assignment. You restrict your mu on the subset A, you get another measure, and you do the integration over there, okay, as an integration over A, all right? And another notation is really just the integral of f d mu. This is just really integration of over the entire space, okay? So sometimes you will also see that. So when things are, the context is clear, usually that's why we don't write the subscript x here. Okay, so here x, usually you will omit this. All right, so this video, the goal of this video is to prove some basic property of this new definition of a integral of a general measurable non-negative function. All right, so this is the main proposition I'm trying to prove. So first of all, last time we defined a integral-ish function. I call it I of phi for simple functions. And I first want to prove that the integral of the simple function as we defined in this new way coincides with the I function we defined from last video. And second, I want to show that if you scale some positive function f, so here f again is measurable, f positive, and you scale it by some c, a constant c, non-negative, then the integral, you can move the c outside. And finally, I want to show that if you have two things that's one less than the other, okay, f and g are both positive, then their integral is also monotone. So the integral of f is less than the integral of g, okay? You may notice I didn't really prove the additivity, okay? So I didn't prove the integral of f plus g is the sum of the integral, okay? So in fact, this is a quite difficult proof, okay? So in fact, if you just follow the idea, you will find that the greater than equal to part is fairly simple, okay? It's just follows from the definition. But to actually show it's equal, you need quite a lot of effort, and by doing that, essentially you're already proving the next main theorem we're going to prove. So I'm going to leave the additivity, or this last piece of linearity to the next lecture, all right? So let's start with item number 1, okay? So I want to show that if phi is simple, then this integral is equal to the I of phi we defined. Okay, this is, let's use the definition. So by definition, I of the integral of this phi is just the supremum of all the, let's say, I of psi, where psi is a simple function that's between 0 and my function phi. So here psi is simple. So from last video, we saw that I function is monotone. So here I of psi will be less than equals to I of phi for all psi less than equals to phi. Okay, so they're both non-negative. So one immediate thing is you're taking a supremum of a bunch of things that's less than equal to I of phi. So the supremum is again less than equals to I of phi. All right, so that's really simple. And you want to do the other direction. Well, the other direction is also very simple because phi itself, okay, so phi itself is a simple function and is sandwiched between 0 and phi. Okay, so one of the simple functions psi in the supremum is actually phi itself. Okay, so the supremum, of course, is greater than one of them. Okay, so this supremum, this integral phi of d mu is the supremum over a bunch of them is greater than or equals to one of them, which is I of phi. Okay, so you prove both direction and you get the equality. Okay, so for simple function, the integral of the simple function is exactly what it expected to be. All right, for the second property, I want to prove that when you multiply a scalar, you can pull out a scalar. Okay, so let's write it out. So integral of c times f d mu. Well, by definition, this is a supremum of all the I of, let's use phi again, where the 0 is less than equals to phi and is less than equals to c times f. Okay, so here phi is simple again. Okay, so, well, if phi is a simple function that's between 0 and c times f, well, let's assume for now that c is non-zero, because when c is equal to 0, then you get 0 on both sides. So you can just divide everything by 0, so you can say, well, let's divide this by 0. So phi is between 0 and c times f is no other than 1 over c times phi is between 0 and f. So here phi is simple, so 1 over c of f is also simple. So you're basically just scaling everything by 1 over c, so simple function is preserved. And now you can just look at this I of phi. Well, you want to pull out the c there, so you can write it as the following. You can write it as, so treat 1 over c times phi is the new simple function. So this is really c times 1 over c times phi. And the last time we saw the I function is linear, so you can pull out the c here. So this is 1 over c phi. Okay, and c times whatever, you can pull out the c outside the supremum. So this becomes c times the supremum over all the I of 1 over c phi, where 1 over c phi is simple and is sandwiched between 0 and f. Okay, so 1 over c phi is simple. And now 1 over c phi, you can just give it a new name, let's call it psi. So you replace everything of 1 over c phi by psi. Well, you notice the right-hand side, the supremum is really the definition of integral of f. So this is c times the integral of f d mu, as we expect it to be. All right. And so finally, I want to prove the monotone. Okay, so third. So if f is less than or equal to g, I want to show the integral of f is less than or equal of g. Okay, so again, this is really simple. The integral of f d mu is equals to the supremum of all the I of phi, where phi is sandwiched between 0 and f, and phi is simple. And you may notice because f is less than or equals to g, so for each such phi, if phi is between 0 and f, then it's certainly between 0 and g, okay? So in particular, because it's a simple function between 0 and g, we know that I of this phi is less than or equals to the integral of g d mu, okay? Because the integral of g is the supremum of all these I phi where phi is between 0 and g, and now I have a particular one that's between there, so I phi is less than or equal to integral. And I take the supremum over the left. I got the integral of f d mu, because it's the sup of all these I phi, I get is less than equal to the integral d mu, all right? So these are really simple proof. And I just want to briefly talk about the linearity at the very end. So in fact, we can, with some minimal effort, we can show that the integral is something we call the super additivity. So it's greater than or equals to the integral f d mu plus the integral g d mu, okay? This is actually quite elementary. The other direction is the harder part, okay? So if you want to prove it, I'm not going into detail because we're going to prove the equality anyways later on. I'll just sketch a proof. So the idea is you pick a psi which between, well, phi between f and 0, and you pick psi between g and 0. You pick it close enough so that it's approximate very well. Well, you know it's less than equals to the integral because the integral is the supremum. But you can always pick something that's not too far away. So let's say minus epsilon over 2. And you do the same thing for psi. Okay, so this is less than g d mu and greater than or equals to integral g d mu minus epsilon over 2. Okay. So now, because of that, well, when you add things up, you can get phi plus psi is less than or equals to f plus g. So it's again, this is a simple function that's sandwiched between these two values. And what we can see is that I of phi plus I of psi. Well, on one hand, I know this is by the linearity of the I function, this is I plus psi. I know it's less than or equal to the integral of f plus g d mu, because f plus g d mu, the integral is the sup over these. But on the other side, I got this the integral of f plus the integral of g, and I minus a 2 of the epsilon over 2, so minus 1 epsilon. And because epsilon is arbitrary, this basically, we can let epsilon goes to 0. That proves the integral is super additive. So this is greater than or equals to the integral of f plus the integral of g, okay? But on the other hand, if you want to show the other direction just naively, so you need something like, I pick a phi that's between f plus g and 0, and you want to break it, you want to somehow break this into something that's psi 1 plus psi 2, where psi 1 is less than or equal to f, psi 2 is less than or equal to g. But there's really no good way of doing this, okay? This is actually not very likely, okay? This is not how it's going to work, so let's just ignore that. That's where the main difficulty comes from, okay? So there are some way of proving this directly, but again, we're going to prove in the next lecture, we're going to prove the monotone convergence theorem, and it follows nicely from the monotone convergence theorem.